right, statistics, it's your last e-learning day of the school year. We are going to work on our 7.3 notes, and we're going to finish through part 2 today. So we're focusing on tree diagrams, and we've done a little bit of this. Sometimes I'll show you a tree diagram to help make sure you're getting all the sample space. We're going to add probabilities into the diagram. So we're going to toss 2 coins. All right, when you toss the first coin, you're either going to get a head or a tail, right? What was the probability of each of those things happening? Well, you had a 1 out of 2 chance of getting a head, and you had a 1 out of 2 chance of getting a tail. Okay, with the second toss, after you got the head, you could get another head, or you can get a tail. And each of those had a 1 out of 2 chance. No big deal. If you happen to get a tail on the first toss, you can either get a head or a tail on the second toss. And each of those had a 1 out of 2 chance of happening. So we have 1, 2, 3, 4 outcomes, and we can follow the path to find each probability. Let's see, it's asking for the probability of 2 heads. So I'm going to highlight the path for 1 head, highlight the path for 2 heads, and then it's 1/2 times 1/2. So you have a 1/4 chance of getting 2 heads. Okay, with coins it's super easy because all 4 of these outcomes were equally likely. But this gets more complicated. If we're looking at cards, we have a deck of cards, 52 cards. We're looking at the probability of getting 2 hearts. So we're going to draw 1 card. It doesn't say anything about putting it back. And then we're going to draw a second card. On your first card, you could either get a heart or something else, not a heart. Spade, diamond, club, anything that's not a heart. Right? And what's the probability of getting that heart? It's 13 out of 52, or 1 out of 4. What's the probability of getting that not heart? 39 out of 52. Okay. Then for the second card, so let's say you picked a heart the first time, you could get a heart again or a not heart, but the probability is changing. Because if I picked a heart the first time, now there's only 12 hearts left in the deck out of 51 cards left in the deck. How many not hearts are left in the deck? Still 39, because we picked a heart the first time. But now there's only 51 cards. Okay. For the second, you picked a not heart the first time, you got a heart or a not heart the second time. Well, our probabilities are different. How many hearts are left in the deck if you picked a not heart the first time? There's still 13 hearts left, but only 51 cards. How many cards in the deck are not hearts? Well, you picked one of the 39, so now there are 38 not hearts. So it's 38 out of 51. So if we wanted to find the probability of 2 hearts, we got to get a heart on the first card and a heart on the second card. So that is 13 out of 52 times 12 out of 51, which as a decimal is about 6%, 5.9%. Okay, so not a very good chance of picking out 2 hearts. All right, so that's an advanced tree diagram, and you can use that to find any combination of things that you want. Now, notice we multiplied right there. We're going to talk about the multiplication rule. The probability that events A and B both occur can be found by using this rule. So this is an and. The probability that A and B happen, that means they're happening at the same time, is the probability of A times the probability of B given A. To find the Kirschner. So let's see if it works for this heart example. Probability of 2 hearts. So P of heart and heart. So the probability of drawing a heart, so I'm doing P of A, was 13 out of 52. The probability of getting a heart, given we've already gotten a heart, so this is the second round, was 12 out of 51. Because we'd already drawn one heart, we'd already drawn one card. So then we multiply those, and that's exactly what we did up above. So it does work. The trick is this second round, the second branch, is a conditional probability. Ooh, and here's a formula to find that conditional probability. B given A can be found by using A and B divided by A. Okay. If we have 35% of the residents in Danville read the newspaper and 20% read the News Gazette and 5% of these residents read both papers, draw a Venn diagram. Okay, so we've got News Gazette, commercial news, and we want to find the probability of reads News Gazette given they read the commercial news. So start in the middle. 5% of the people read both. 20% read the commercial news, but we've already counted 5 of them. Nope, that's backwards. That's the News Gazette. 20% read the News Gazette. But I got to take out the 5. So the whole News Gazette circle needs to be 20. 5 and 15. The whole commercial news circle needs to be 35. So that's 30. Okay, drop in P of B. Reads News Gazette given they read the commercial news. So with a Venn diagram, this is fairly easy because we can just look at given they read the commercial news. So I'm only looking at that circle, given they read the commercial news. How many people read the News Gazette that are in that circle? 5 of them out of 35. Five out of the 35% read the News Gazette given that they already read the commercial news. P of B given A. So that's with the Venn diagram. Let's see if it works with the conditional probability up above. So it would be P of B. So let's call this one. This is A. Commercial news is A. News Gazette is B. So probability of B, A, and B over P of A. Just copying that from above. So probability of commercial news and News Gazette was 5% over the probability of A, which was the commercial news, which was 35%. Hey, look at that. It's 5 over 35. So you can either draw a picture, help you guide it out, or you can use the formula, which I will give you on the test. Okay, that multiplication rule works for everything. If the things are independent, like they don't influence each other, like drawing a card and rolling a dice, then you can just multiply them both because there's no overlap. Because that means that that second event in the tree diagram didn't change. It's like when we did the coins and it was just 1/2 times 1/2 because there was nothing to change about that second flip. So that's what's happening here. Let's see, Mrs. Morris is awaiting a kidney transplant. Mr. Morris. His doctor gives him the following information: 90 survive, 10% die. Transplant. These were 60% of those who survive, and the other 40% must. Mr. Morris wants to know the probability that he will survive for 5 years. Okay, so we're going to start with the first piece of information. They're getting the transplant, so 90% survive, and then 10% don't. 90% survive, 10% die. Okay. The proportion, if the transplant succeeds for 60% of those who survive, and the other 40 must go to dialysis. So, like, we're done on that bottom one because they're dead. But for the people who survived the transplant surgery, 60% keep going. 40% go back on dialysis. Okay. Then the proportion who survive for 5 years are 70% for those with a new kidney and 50% for those who return to dialysis. All right, so this is the new kidney path up at the top. 5-year survival. 5-year. 70% of the people who have a new kidney survive 5 years, which means, what happens to that other 30%? Because these have to add up to wholes. They didn't survive 5 years. For those who are on dialysis, 50% lasted 5 years, which means 50% didn't. Morris wants to know the probability he will survive for 5 years. Draw a tree diagram to represent this information. So, there's 2 ways that he can survive 5 years. There is, go away, this path, right there. And there is this path. So we're going to find the probability of both of those. Okay, path 1 was 90 times 60 times 70. Which is about 0.378. Path 2 is 90 times 40 times 50, which is about 0.18. So both of those are good. We're going to add them together. 0.558. So he has about a 56% chance of surviving 5 years on a transplant. Okay, now how do we turn this into a two-way table? Well, we've got, we're not going to worry about turning this into a two-way table because I feel there are 3 categories. That would be a 3-way table, and we don't know how to do that. Okay, so here are your basic things. Like, you can just multiply probabilities if they're independent. If they're dependent, like on the cards, you have to make sure you've accounted for the change. So you either use the formula or, like we did right here with the 12, we accounted for the change. But that multiplication rule will help you on that 7.3 assignment that is posted as your work for today. All right, guys, I will see you on Monday. We'll review chapter 7, and we'll still have that test on Tuesday.